Okay, so you see that when x is equal to 1, that's when I go in here. That's when x is equal to 1 is when I approach this point in here. When x approaches 1, z approaches, x approaches 1, z approaches 0, so you approach this point in here. And when you look at this thing here, well, the relation between z and x, the mapping here from here to here is radial. This is just a unit vector, so z hat and x hat are the same. So this thing here is just a projection. This thing here is actually a projection on the tangential direction. This thing here is a projection on the normal direction. And so it says when you look at this thing here, when n is equal to, it would be 2 or higher, the normal direction always has an eigenvalue here that is actually 0. So you will always have conductivity 0 in the normal direction in here. So it's going to be degenerate as conductivity 0. But if you look at this thing here, when n is equal to 2, this thing here is minus 1, so when z goes to 0, this goes to infinity. So this has conductivity, so as you are in at the ball of radius 1, you have conductivity 0 in that direction, and you have conductivity infinity in the other direction. Not only are they highly anisotropic, but they are as degenerate as they come, because it conducts like 0, and it's a complete insulator in that direction, and it's a perfect conductor in the other direction. That's very hard to construct. But that's how the construction is. And so that would be the material. This would be the material in here that would render anything in here invisible. Now, why does it make anything in here invisible? It does it for the following reason, that you can think you have your solution over here to the Laplacian. Well, it's a Laplacian except for a point, but of course we know that if the solution is bounded, then a point is a removable singularity. So over here it doesn't really matter. But over here, what is it that happens as you come in here? Well, the value that you have of your solution here gets taken to live here. So that means that the solution is constant on this curve, which means the solution is constant inside. And what is it you are solving inside? You are solving divergence A grad U inside, right? That's what you want to solve for A. But if U is constant, then the gradient vanishes, and no one can tell from that solution what UA is. So really the secret to this is construct something that is sufficiently anisotropic, sufficiently degenerate with 0 and infinity, such that the solution becomes constant everywhere here, and then no one can tell what you have inside. But that requires go very highly anisotropic and very degenerate. And that's where I now want to take the last 10 minutes and see what could you do to sort of get rid of that. What could you, how could you get something that is not degenerate and anisotropic in this sense? And so, are there any questions at this point? Okay, I will then show you just, so what I've shown you in the next slide is actually take a ball of radius rho. And now take a ball of radius 1. So now, do the following, the mapping that I showed over there. This is a ball of radius 1. Take this one away. This mapping that I've taken down there, this mapping here, maps a ball of radius rho. Device just dilates that one so it maps it to the ball of radius 1. This is a mapping, again, it's a radial map. It's a linear map there. So it actually maps radii here onto radii here, and it has a property that when x is equal to rho, so when you're down there, when x is equal to rho, this is 2 over rho plus rho, this is 2 minus 2 rho, so you get 2 minus rho, or 2 minus rho, you get exactly 1, so it maps that to 1. It maps the outer boundary when x is equal to 2, it maps it to the outer boundary 2. So this is a mapping that maps this domain onto this domain, maps B of rho onto B of 1. And so now what you can do is you can take one here, the one that you have, and map it forward and say this should be F rho star of 1. So now you have something, this thing here, This is a perfectly nice map. This does not blow up anywhere. It's a Lipschitz map. So when you take it over here, everything is bounded. You don't have the problem of anything becoming infinite and zero. What happens is, of course, when you send rho to zero, you get to the point. So the degenerate situation that I took before is by letting rho go to zero. Then you have perfect cloak. So the question is, for a finite rho, what kind of cloaking do you have? You don't have that u is equal to u tilde, because the Dirichlet-Neumann data maps are not exactly the same, but you could say how far are the Dirichlet-Neumann data maps from each other? And that's exactly what goes into this other sort of regularized cloaking. And that's what I want to show you. So you have now this mapping. You have over here, you have your approximate cloak. This is what I would call sigma c rho. That's your approximate cloak, and it's just a push forward of 1. So over here you have 1, you push it forward, you get it here. Inside here you're trying to hide some coefficient a that you want to hide. And of course that corresponds to something over here that would be f rho minus 1, then mapping in the other direction, pushing it back so you get something in here that no one knows what it is, but it's hidden inside there, or it's sitting inside there. So now if you want to know, this is the coefficient you have over here now is 1, and you have this mapped back. If you took this situation where you have this coefficient here and this coefficient here, you have that this A sigma A here and this sigma rho here, they have the same Dirichlet-Neumann data map. No doubt about that, because they're just a push forward of each other. The question you can ask is, how far is this situation here from the situation with 1? So if I have 1 out here and I have a small hole of radius rho, where I have something inside that I have no control of, because it's whatever you want to hide pushed back. But the only thing I know is geometrically it sits inside a small set. So basically what I'm giving you is I'm saying you are permitted to hide things in a big set. I'm going to transform that big set into a small set. And my cloak here will be the one that corresponds to 1 over here. So I'm going to transform the cloak plus what you are hiding into a 1, and then something that's unknown inside. That's the back transform of what you're trying to hide. And my real question is to find out, since the Dirichlet-Neumann data map of this is the same as the Dirichlet-Neumann data map of this, my real problem is to find out how far is the Dirichlet-Neumann data map of this from the Dirichlet-Neumann data map of 1. Because the Dirichlet-Neumann map of this is equal to the Dirichlet-Neumann data map of that. That's just saying this and this have the same response. But what I really have to find out is I have to find out how far is in the Dirichlet-Neumann data map of this situation over here from the Dirichlet-Neumann data map of 1. Meaning if you have a small inhomogeneity and you have no knowledge of what's inside, how far is that from not having an inhomogeneity at all? And you might suspect that, gee, how far it is depends what's stuck inside this little inhomogeneity, because the only thing I've done is sort of a fake mapping, right? But this is the wonderful thing, is that this is bounded by a constant that does not depend on what you're hiding inside, but only depends on the radius of the set. So a small inhomogeneity, in this case here, the only way it's felt is through its volume, not what you put inside. And the way you can understand that is because if you put a small inhomogeneity that is perfectly insulating, or one that is perfectly conducting, they each have a response of the form rho to the n. And so anything in between would there would be a monotonicity result, and you can bound it by a constant times the volume. And so this really tells you that I have constructed a cloak over here where you can put anything inside. It's going to look like just the 1 coefficient up to constant rho to the n. When you send rho to 0, you're going to get perfect invisibility. The Dirichlet-Neumann data maps are the same. And for a fixed rho, I can tell you exactly how much invisibility you're going to get. And the advantage is that this thing here, it's anisotropic, so it conducts differently in different directions. But it is not singular, because it's a perfectly finite Lipschitz map, and so it doesn't have 0 and infinity eigenvalues. It only has finite eigenvalues. And so that's why you can now start doing these kinds of estimates. You can start, and I think I I would then just maybe discuss for 2 minutes here. You could do these kinds of estimates. So this says, how far is the directly Neumann data map from the directly Neumann data map for 1? And you get estimates that says it goes to 0 when this parameter goes to 0. Now what is a parameter? The parameter is a measure of this set here. It's a measure of the set that you have over here. So it's not really a sort of, it's a little bit of a fictitious parameter, because you could say, well, if you want something that's smaller, you just take this set to be smaller, right? You can make this set as small as you wish, and you get exponential convergence, right? But the thing is, the set here, how small the set is, determines, and so that's what maybe I should show you here. If you so here what I have done is I'm in 2 dimensions, and I've said that my sigma c rho, this is now a matrix, this is f star of 1. This basically, when I diagonalize it, it has lambda max and lambda min. So these are the eigenvalues, right? This is the eigenvalue, the maximum eigenvalue of that and the minimum. If I want to find out how anisotropic this is, I divide it, and it behaves like O to the rho minus 2, which says that the smaller rho becomes, the more anisotropic this matrix becomes, but it never becomes infinity and 0, it becomes of the order of rho minus 2. So really, and if I took the mean of this, not the maximum of this ratio, but the integral of this ratio is rho minus 2, rho minus 1, it gives you an idea of, this is what it tells you how hard it is to construct this material, because it's very hard to construct materials where one eigenvalue and the other eigenvalue are 2 orders of magnitude apart. Like if rho was a 10th, this would mean that there would be 100 difference between the 2 eigenvalues. It's very hard to construct. And so it should be in terms of this, in terms of the chi max and the chi mean, that you should measure not in terms of rho, but of course here you have the relationship between rho and chi max. It says that chi max is equal to 1 over chi max, the square root of that is equal to rho. And so if I go back to this estimate here, it gives you rho can be measured in terms of